So I will present two journals for this session. The first journal will be Computer Methods for Automating Preoperative Dental Implant Planning, Implant Positioning, and Size Assignment. It was conducted by Galanis et al. So I will talk about the introduction, background, method design consideration, method implementation, case study and discussion, and conclusion. The introduction. Computed tomography is aimed to support preoperative planning towards a safer and more predictable treatment outcome. There are advantages such as enhanced visualization capabilities of the anatomical case, accurate measurements, data processing of optimum implant allocation and size selection, and inclusive documentation of the patient treatment. In this paper present a computer-aided methodology that aims to a systematic dental implant planning approach based on appropriately processed CT data. We move to the background. The limitation of conventional pre-implant treatment planning, which is based on 2D radiographs, has been overpassed. Aesthetics and morphology considerations for implant positioning are integrated by using CT image. There are several commercial software such as Implant, Nobel Guide, Co-Diagnostics, Implant Master, and Med3D. Virtual reality technologies have also been used to improve the patient image interpretation and plan treatment performance. CP et al. Introduced a novel approach rendering and modeling of implants which allows interactive 3D manipulation. Kondo et al. Presents a computerized techniques for extracting the inferior alveolar nerve canal. Chukchara et al. Reorients the axial image and generates relative cross-sectional image parallel to the planned implantation axis. There are two consideration methods designed for this study. Implant axis positioning. Due to the rotational axis symmetrical shape of a dental implant, the location and orientation of its axis, and in addition, the location of a reference point on it, fully establish the implant position in the 3D shape. The next, implant size. The space between implant external surface and its surrounding anatomical structure is important for a safe and successful treatment. In implant axis positioning, there are three criteria are introduced. First, uniform geometry distribution of the bone volume surrounding the implant axis. Second, uniform bone density distribution surrounding the implant axis. And third, uniform geometry distribution of the provisional prosthetic superstructure volume around the implant axis. On the other hand, implant size have limitations should be taken. First, adequate space of at least 1.5 mm between implant and jawbone's external surface. Second, adequate space of at least 3 mm between implants or between natural teeth and implants for proper integration. Third, for mandible case, adequate space of at least 1 mm between implants and alveolar nerve channel. The method implementation data will be pre-processing, and there will be region of interest and derivation of the implantation axis, and next, implantation dimensions. There will be implant placement, planning safety validation, bone quality and quantity around the implant. From the CT data, information regarding image and pixel dimensions, slice thickness and location, grayscale resolution depth is extracted. Background soft tissue which is irrelevant to planning is removed by means of a thresholding operation, as you can see in the picture. Region of interest definition is controlled by the prosthesis which satisfies aesthetical and functional requirements. In the picture A, as we can see, region of interest designation by a sketched quadrilateral around the contour of restorative tooth, and the picture B, 3D representation of ROI designation. In this image, processing steps for extracting and mandible arch geometry and segmenting bone region of interest. In picture A, an initial axial CT image of mandible at bone level. Next, thresholding for background soft tissue removal. C, binary convection. And next, hole filling. E, irrelevant element removal. F, binary segmentation mask. G, binary segmented bone region. And H, intensity segmented bone region. In contrast, image processing steps for segmenting crown prosthesis area and removing artifacts. In picture A, an initial axial CT image of mandible at crown prosthesis level. B, thresholding for background soft tissue removal. C, binary segmentation mask. D, segmented crown with artifacts. And E, high threshold value for artifacts removal. We move to the revision of implantation axis. The position of implant 3D line axis is obtained using the smallest square regression line fitting method on the centroids of the bone and prosthesis segmented slice. The centroid coordinates for a given segmented slice are shown below. Implant geometry is described as a cylinder of diameter D and length L. An additional distance from the occlusal tip of implant is assigned for the determination of the beginning of implant bone interface, or we can say implant bone level, IBL. The exact positioning of the implant is presented in the next slide. Implant placement. The location of the implant placement reference point is accomplished through an automatic scanning process based on the radial bone quantity assessment. Planning safety validation. It is carried out by calculating the radial distance between points on the implant external surface and points on the mandible surface and points on the mesial distal ROI margins. A sample group of radial safety margins graphs is shown. Sample group of RSM graphs for a 4 mm implant diameter, where L is the distance of the section plane from IBL and Z the coordinates on the axis. As gray are drawn the distance between implant and mandible external surface. White are the regions between implant and mesial or distal surfaces, and black are the distance lower than the limit. Bone quality and quantity around implant. Gravity sampling around implant surface is performed by creating a parametric mesh of points that are found on concentric circles vertical to the implant axis. As you can see, the parametric 3 is for bone quantity and the parametric 4 is bone quality. So we move to case study and discussion. There are 3 posterior teeth in the patient mandible at 36, 35, and 34 are presented and discussed. Diagram images were obtained with the resolution of 512 times 512, slice thickness 0.5 mm, and pixel size 0.32 mm. LIM was set at 1.5 mm both for RSM implant bone and RSM implant mesial distal. The bone quantity and quality index are 1 mm were calculated. The results are presented in Table 1, 2, 3 for the stance at position 36, 35, and 34. For the lower left molar, 36, there was plenty of surround bone margin for the wide diameter implants. The implants with diameter 5 and length 10 or 8.5 presented the 2 highest bone quantity indexes and the highest improvement of bone quality among the candidates of the same length. For the lower left premolar at 35 and 34, the available mesial distal space was found narrow for the 5 mm implants with 3 to 4% negative RSM, and these implants were consequently rejected. Regarding the left lower premolar 35, the implants were with diameters of 3.3 and 3.75 mm presented the lowest risk. For the left lower premolar at 34, the implant number 1 was proposed for presenting the lowest risk of 27%. The conclusion for this study is the developed index for the evaluation of surrounding implant bone quantity and quality are crucial for the method outcome. The alveolar nerve canal and the simultaneous planning of multiple adjacent implants are also taken into consideration, including complex implant geometries. So we move to the second journal, which about implant planning and placement using optical scanning and cone beam CT technology, was conducted by Jeff van der Zel. I will presenting about the introduction, technique, discussion, and conclusion in this study. Dental implant rehabilitation has faced demands from prosthetic and aesthetic areas calling for increasingly ideal outcomes which require precise surgical planning. The technique, as illustrated by a clinical case study, is used to demonstrate the possibilities of the new computer-aided implant planning and placement therapy. There is 8 steps for this technique in this study. First, an impression is made of the implant jaw along with an occlusal registration of the antagonist arch. Second, a modified laser triangulation scanner is used for high accuracy optical scanning of the gypsum surface. The reference markers on the scanographic guide the gypsum cast on the implant jaw and the occlusal registration. Third, the scanographic guide with 3 markers is placed in the patient's mouth during CT scanning and on the gypsum model during optical scanning to obtain a combined 3D view of region of interest, as you can see in the picture. 4. The program then generates a 3D view of the mandible showing the ROI and position of nervus alveolar inferior. The thick mucosal tissue layer at the ROI is clearly visible for implant placement. A virtual implant is chosen from a range of implant options varying in lengths and diameters, then placed in the optimal position according to the critical information defined by designated critical structures and the 3D and cross-sectional views. 6. Two customized surgical guides are designed to accommodate a pilot drill and an end drill. The software generates a virtual surgical guide on the jaw with the planned implant in position. Also shown is the inside of the surgical guide obtained by optical scan of the gypsum model. 7. The surgical guides are produced by stereolithography and fit perfectly. It can be positioned in the patient's mouth in a unique and stable position with a snap fit to transfer the preoperative treatment plan. Last, an abutment is then fixed to the implant with a fixing screw, and a temporary restoration in functional contact with the antagonist is cemented with temporary cement. Kenke described the noble guide procedure whereby small diameter holes are drilled in the bone, after which pins are placed through the guide into the holes to keep the surgical guide in place, while Gabbard describes the surgery guide whereby for the same reason, the guide is fixed to the bone with screws. The present procedure gives a snap fit, which makes a fixing mechanism of surgical guide to the bone unnecessary. The radiation effective dose for a full head cone beam Newton 3D image is the equivalent of about 4 to 6 panoramic radiographs, depending on whether the salivary glands are counted separately. As comparison, the cone beam CT requires 30 to 19 times less radiation than the conventional CT scanner used in the present system. In conclusion, the protocol can enhance prosthodontic-driven placement of implant in a fully monitored flapless surgery. This technique can be expected to flourish as dental implant therapy develops to meet the highest demands of comfort, precision, and safety. Okay, that's all for me. Thank you for listening.